Well, hi, good morning, everyone. I'm Dalin and from Washington University. Thank you for your patience for our technical issue. So no worries, my session is a little short, around 20 minutes, so you still can get your lunch on time. So in my session, I'm going to discuss what's the consideration for the machine learning with the functional near-infrared spectroscopy data. So the contents, firstly, we will introduce the principle and the theory for fNIRS and machine learning, and also discuss the current state of machine learning in fNIRS, and describe the existing machine learning fNIRS application. Last two parts, we will discuss this consideration and the open challenge, and also what's the solution, what can we learn from EEG and fMRI. So after this session, you will be able to know the background knowledge of machine learning in fNIRS field and the existing machine learning fNIRS application and how to analyze that. And the last part, you will know what's the challenging solution and the future directions. So as mentioned with the previous session, fNIRS is an indirect neuroimaging modality to measure the absorption of the oxygenated and deoxygenated hemoglobin from the head. And compare with the fMRI and the EEG. In EEG case, we can measure the brain activity from the scalp. And after that, due to the neurovascular coupling, we can able to see the hemodynamic response besides the fNIRS. And in the fMRI case, we can able to use the magnetic field strength and get the both signal blood oxygen level dependent. So we can measure that by the fMRI. Compared to the fMRI and the EEG, generally speaking, fNIRS can provide the higher temporal resolution than the fMRI and better spatial resolution than EEG. Also have the other advantage like low cost, safe, and is silent. So firstly, fNIRS appeared to 1977 and is tested by the cat model. Later, we applied that in the human model, and in the time we can measure the hemodynamic response in the time domain. Lately, we working on improve the spatial resolution by the multiple channel fNIRS, the diffusion optical topography, diffusion optical tomography, and nowadays the HDDOT, high density diffusion optical tomography. So currently, we can develop like the fMRI comparable image quality using HDDOT. So come to the machine learning. The initial idea for the machine learning is kind of a biological neural model. Like this, once you get some input stimulus and you can make the response. But why this happened? Because our brain already trained mature enough to respond to this kind of stimulus. This kind of the training can be done in the childhood. Besides this motivation, we developed the mathematical model. We gave each neuron kind of the activation function, and we teach them what, whenever get some input, we will output and get the different learning weight. Okay, besides that, that is the basic concept for the neural network. Come to nowadays, the machine learning used everywhere. In our fNIRS field, the first paper appeared around 2011. Until date, is around 100 papers appear, especially last 2 years. I'm so excited to see such of the applications in our field. So we generally divide several categories, something like mental state assessment. For example, you are now stressed or you now hungry, because the different patterns of, regarding the hemodynamic response is able to detect it and to assessment that. So similarly for the brain disease diagnosis, something like Alzheimer's disease and autism or some of the other disease, because these have a different pattern in the brain, so we also can be able to diagnose this. The other main hot area, the hot topic is brain-computer interface. Also, we are using fNIRS to get the different brain signals and encoding that as the output for the control sum device. So the other applications is not much paper mentioned that, but also very interesting, something like reconstruct the brain or tissue model, something like neuroscullar coupling and the denoising algorithm. So today we are going to pick 3 of them to introduce how to use machine learning to do this kind of analysis. So first one is brain disease diagnosis. As we know, the brain disease is always related to some damage, either in the functional or in the brain function or the structure. So normally, the traditional way is diagnosis by the doctor going through a different kind of examination or the scan. But now we are using the machine learning, whether we can use some brain imaging scan and use the well-trained model to do the prediction or not. So generally, the pipeline for the analysis, first we get the brain signals, and after that we do the analysis, get the different features, and then put the machine learning, let the machine learning to learn what's the difference between the disease and healthy control. So besides that, we can get the output, tell you how much percentage confident you should determine these people is patients or not. We also have the other pipelines, that is the feature extraction part we omit. So nowadays mostly using the deep learning part. So this is the paper come to 2016. They use for traumatic brain injury detection. So in this paper, they made the fMRI response in terms of the HBO signals, and they have the multiple channel. They ask the subject to do the different kind of mental task. They come to the feature extraction part, they focus on specific task, and you are able to get the activation start time, also the peak amplitude, and also area under curve, and also something like the slope and left part or the decrease part. So besides that, you can get several features besides the fMRI response in the left part, and put the features to the classifier. In here, they use the decision tree. So that's the basic idea is we are teaching the decision tree, use a different feature. So put in the feature and for example, some threshold, if we lower than this threshold, that means this is the TBI patients. If not, so this may be the healthy person. So after train this model, they can be we get the new data inside, put inside, and then you can get the prediction. So because we know what's the real, this subject is patient or not, so we can get the predicted value and the actual value. If the predicted value is, for example, is a healthy person, and the actual value also the healthy person, so we call that is a true negative. And also, if you predict is a patient, but actually this no, is a healthy person. So that will be, we call that is false positive. So besides this confused matrix, we can able to we can calculate the accuracy, sensitivity, and the specificity. So left part you can see they get the different accuracy, use a different feature. So you can see different feature get a different accuracy. That's depend on how much this feature can be used for distinguish the patients and healthy control. They also combine the different feature and to do the analysis. So they are not only dependent on one feature, they combine different feature and you see the accuracy is increased. And also you may notice, so we don't know which kind of feature we should use because we are not sure which feature will working well. So that's the reason nowadays, as we mentioned previously, the feature extraction step they omit, and they will put it to the machine learning. Let the machine learning tell us, okay, which feature is good, which combination will be good. So that is the motivation for the omit the feature extraction part. So come to the brain-computer interface. This is also very hot topic. So the basic idea for brain-computer interface is to track to the brain activity and to decode as the control command for the outside computer or some of the other device. So as you may know, they have a lot of the BCI types. They may use EEG, ECG, MEG, or some EMG, also as well as the fNIRS. As we mentioned previously, fNIRS may compare EEG, we have the less motion artifact, so with the moderate temporal resolution. So here is the example which I borrow from the Dr. Kahan and my old advisor, Professor Kim Chi-hong, and they did some brain-computer interface system to control the quadrupter. So in this case, they met the fNIRS signal and the EEG signal together. So as they put the electrodes and the optodes in a different position. So they also ask the subject to perform different tasks. In fNIRS, they ask the subject to do the mental counting, mental mass, mental rotation, and water generation. In the EEG case, they ask the subject to do eye blinking and eye movements. So they repeated this task several times. And here they have the very wonderful ideas, because in the fNIRS case, normally if you want to do the channel region of interest, you select the region of interest, you should rely on the general linear model. So this is take a long time. You should use whole time series. But in the BCI case, the time consumed is very important, in fact, the index. So in that case, they select the region of interest in the BC line. They have, if the channel is only is different between the BC line value and the first trail maximum value is positive, then that channel will select it. So something in the left side, even though they have 16 channels, but you see only channel 4, channel 9, and channel 10 is satisfy the criteria. So they select that for the further analysis. So they compare with the t-value BC, the method. So they can say some of the not all the channels selected, maybe partial of that, but the time consumed is reduced a lot. So this is the ideas. So you can see the right part, this is the different hemodynamic response. They can select in the different task, distinguish the different tasks in 4 seconds. So eventually, you can see the left side, the EEG and fNIRS, they totally generated 8 commands, and each task related to the different movement. For example, you can forward, rotation, or the takeoff, landing, something like that. So actually, here is video, but I'm not sure I can play it or not. Oh, I cannot, sorry. So yeah, actually the middle part is the video, so they can able to control the quadrupter in a different direction. So the right part, they draw the trajectory for the quadrupter movement. So they design the trajectory, but you see some of the subject can control the quadrupter perfectly, but some of that maybe not. So eventually they get the accuracy in the fNIRS around 76%, but in the EEG case it can reach 86%. The why this happened, I think the main reason is because the time is so short for the fNIRS case. So if you do the BCI part, use the fNIRS, you always be struggling to trade-off. Either you choose the long-term window or you want the shorter window with the lower accuracy. So this is the issue VT has to address. So the other core application is neurovascular coupling. So as we mentioned in the previous slides, the hemorrhagic response measurement be seen on this underlying mechanism. But normally we just use that. But how that happened, why this new activation transfer to the cerebral blood flow change? So that's is still unknown. So this is also the core study appeared 2019. They measure the EEG and fNIRS signal, and they use a deep learning model and to predict this underlying mechanism. So this is the structure. So they firstly get the time domain EEG signal. They put it to the convolutional neural network and get the vectors as the input to the auto encoder. So something like, you get the main features and use this main feature, put the decoder, and then you can recover the vectors, important vectors. And after that, they again put the convolutional neural network, and then you can restructure the fNIRS signal besides the measurements structures. So the idea is, they didn't mention why they designed like this, but in my opinion, they designed this, for example, the middle part in here. So they somehow like the source event happened, and use this backward structure, so you're able to get the EEG measurement. But the same vectors, the source event here, and you also able to get the fNIRS. But the middle part is something related to the underlying mechanism related to the neurovascular coupling. So this is the core study. Let's see the results. This is the measurements for the fNIRS signal. The black signal is the measurement, and the red one is the prediction using EEG signal. So you can see it's very correlated with each other. So they also calculate for each patient and get the reconstruction error. That is besides the difference between the measurement and the prediction. So as we know, the EEG have a different kind of the frequency band, and they use 5 different the brain waves to do the prediction. They found that the gamma wave is more predictable. That's maybe because the gamma wave is more related to the cognitive function, and the delta is something related to some sleep or some very quiet state of the human activation. So that's maybe the reason. And then they again validate to use the functional connectivity. You can see in the measurement part, the fNIRS signal, you can see some event happen in some specific cortex. In the prediction signal, they also can get that similar pattern. So that is a very interesting topic. So definitely they have the other machine learning applications use fNIRS signal. So, but we are not going to see the detail. But briefly, something like hyperscanning investigation, they use machine learning to predict, and something noise removal and image quality enhancement also can be used, and something like kids development prediction. Something like the mental state monitor, and also we mentioned the tissue model reconstruction, also very cool area. So considerations for the machine learning fNIRS. So after going through this, you may ask, okay, whether machine learning is really useful for the predict the disease or not, compared with the doctor's diagnosis. So the answer It's harder to say, but you can see use of machine learning, you can achieve the higher accuracy. For example, the autism, you can around 95, Parkinson's disease diagnosis, you can maybe 97%. Similar with the sensitivity and the specificity. Yeah, this less is high accuracy, but also we have the lower, less computational power. Yeah, also efficiency, right? But also why recently still didn't use in the clinical, because somehow the machine learning still like the black box. Even with this classification we did well, but we cannot explain why that's happened. So that is the question here. The other question maybe, okay, is will be the future of what's the future of the healthcare and how it will affect the human being. So I think maybe so far there is still a question here, but that's it, the future. Maybe, yeah, future we can maybe use kind of this AR-based method to do these kind of core applications. Yeah, that's it, the future. And the other question maybe say, what's the role of the machine learning to the BCI system? I think that's is essential. Because now most of the BCI system is use the machine learning, especially the deep learning model, to do the prediction. But how to do that more efficiently, especially in fNIRS case, use a short time window to do this also is the good question to think about that. Last part, we are thinking, so this is really beneficial to use machine learning to do the model, brain model reconstruction or something neuromuscular coupling investigation or not. So I think that is a very core application. Because normally, as Adam or Hamid already explained, so normally we use the diffusion equation to reconstruct the model. But BC, there's so many assumptions, right? But in the machine learning, maybe we can do some different kind of prediction. But one issue here, in the tumor detection, they did well because the tumor is fixed there. But our brain signal is somehow functional, is dynamic. So whether it can predict this pattern or not, also not sure. And for the neuromuscular coupling, I think that is a very cool direction, because normally people just use the linear correlation to generally related this mechanism, but I don't believe the neuromuscular coupling is simple like the linear model. So maybe use machine learning or deep learning, we can do some the other dynamic level prediction. Okay, so what can we learn and borrow from EGFNIRS? So especially for the brain disease diagnosis case, we have so less sample size. So that's made the prediction maybe well, but whether it can really use in clinical or not. So that is the main issue there. So in the EG case, they have a lot of the data set and the open source. So, but in the fNIRS case, so far there is no much open access data set for the machine learning toolbox development. So, and the other issue here, so because even have some open access data set, but they have the different data format, or some from different device, we cannot use two kind of a data set for train one machine learning model. So that is also an issue. As we mentioned also, we so far don't have the machine learning BC, the toolbox to do this kind of either diagnosis or detection. So if we have that, we can validate together and then make that more strong. So so far you can see a lot of the fNIRS and the fMRI study. Also, they have the EGF-fNIRS combined study. That's also the direction. They combine the two kind of the modality. They always say they have the higher performance. Maybe this also the way we should go. So this part we are going to, so whether fNIRS contribute to the human brain mapping or not, how much we can contribute. So as we know, EEG and fMRI, we always consider it gold standard to the brain mapping. But fNIRS actually also play a very unique advantage, specifically in the no space limitation and compare with comparable fMRI image quality, and provide the other brain information for the temporal resolution. So for example, in this study, they use for do the cerebral neural monitoring during the surgery. So you use the fNIRS signal. So in that case, fMRI cannot do. And the EEG case, maybe we can get some temporal information, but in the HDDUT case, we can either get the time domain signal information, also get the highest spatial resolution imaging. Yeah, that is the HDDUT can do. And the other one, as EEG, is, yeah, we admit that they have the good temporal resolution, but due to the conductor volume conduction, so we cannot do the source localization. So in that case, fNIRS can do that. And also, they have the core study. They say use the fNIRS to inform EEG source localization. So yeah, this also help EEG. We can get two temporal and spatial domain information together. Yeah, so that's it for this part. And yeah, for the last part, yeah, we still have so many issues. We are waiting for future direction. So something like fNIRS always struggle for the much more deeper sensitivity. So recently, we also developed several different kind of methods to do that. So it's also cool to dig with more deep structure, so we can see how deeper we can go with this modality. And also, signal to noise ratio is always the headache problem. So yeah, still we should working on in this field. And the other one, we do the special the head modeling. Normally, we just borrow the general model. How to customize that for each participant, for each subject, also is a very cool topic. So overview for this morning's session. So you already maybe know the fundamental knowledge for the NIRS, and also know how to collect the data and do the quality control, and also know how to processing the data in the time domain and the spatial domain. And also Lisa talked us about the other NIRS-related modality, diffusion correlation spectroscopy. And also last part, we all know, okay, after we get a signal, how to utilize that in the clinical or the daily life purpose, especially along with the machine learning. So that's all for this half-day session. So thank you, everyone, to attend. And if you have any question for 6 of us, you are more than welcome. Thank you.
Thank you so much, Dalin, for wrapping everything up so wonderfully. I just want to put up, who knows if this will play. Here we go. So we have a link. I don't know if the dark blue will show up. Any of you that have a phone can take a picture of the QR code. If you have questions, you can ask now. We also have the link through there has various feedback opportunities to tell you how much you loved us managing the HDMI cable this morning, and other components of our course. and other questions that you may have and opportunities for follow-up with any of the 6 of us. So please, please, please visit that page and help us optimize the next round and get some feedback and engage with you in conversation. We do have 0 minutes left. I mean, I'm happy to stick around and answer a few questions. I know it's noon, so this is officially the end of our time. Apologies again, and thank you so much for your patience as we dealt with all of our unexpected HDMI AV issues this morning. But I think I really appreciate my great team for helping get through this kind of very large fire hose set of course objectives to kind of get through and communicate the underlying physics as well as processing all the way from the ground up to machine learning for some of what we're working on as a community. So I welcome any of you if you have any questions. Otherwise, we can all go get some lunch. Any questions, anybody? Also, we'll be around all week, or at least half of us will be around for the extent of the conference. Yes, do you have a question? Okay, well, feel free to come and grab any of us today or throughout the rest of the week, or shoot us emails as well. Anyone want to ask anything while we are all here together? Yes, please. Oh, I'm sorry, do you mind, you could use one of the microphones if you like? Yeah, there's a couple over there.
Is it working? Oh, I just have a very brief question, like how for the fNIRS, and I'm just wondering, is it possible for people to wear them during sleep, or like how long the measurements could be, and is it comfortable? And the question like this, yeah.
That's a great question. Kara, do you want to take a shot first?
Is it working? Yeah. Yeah, so I can just testify on the fact that my 15-month-old back then son wore it for like 2 hours while he was sleeping on his buggy, in his buggy, and it was absolutely fine. He had no mark on, so, and the cap that I showed you also had EEG embedded to account for the sleep stages. Yeah. So I think that's absolutely doable. I don't know if there are studies that did that like over a whole night. I don't know if my colleagues know about that. I think there are.
Yeah, there are a few groups that are engaged in the overnight sleep studies. It's a really, really great question. It's really hard to get people to stay asleep and go into REM and, deep wave and fMRI. So we had a study that we presented at HBM a couple years ago and are still trying to get it out, where we actually had 8 people do 2 full night sleeps wearing the high density cap, as well as EEG to do the polysomnography and whatnot. So those are 8 hours, multiple sessions. And we have other non-sleep, but during surgery that are 6 to 8 hours long as well. So a big part of it is system design and making it comfortable, but that's absolutely a big part of the development multiple systems are working on.
Yeah, thank you very much.
Mm-hmm. Great question, thank you. Yeah, please go ahead.
Hello. So I have first a quick question for Chiara, I think. You mentioned HOMA 2 as like the first tool we should go for. HOMA 3 has been around for a while. Is that a choice that you just mentioned, HOMA 2?
Yeah, so that's actually a good question. I think in HOMA 3 they changed a little bit the GUI. So a lot of the fNIRS users are still very much attached to HOMA 2 just because it's like that's what I've been using. But to be fair, all the functions inside are exactly the same. So if you're new, then feel free to start with HOMA 3. It's absolutely fine. And the fNIRS community and forum that I mentioned is completely valid for both of the versions. So if you're new, then maybe it's a good choice.
No, I'm not new. I'm old, actually.
Okay. Yeah, and then yeah, it's absolutely exactly the same. They just change a few things on the GUI, on the visualization process, and I think they integrated a couple of new functions, but what was in HOMA 2 is exactly, the core functions are exactly the same, so it won't change anything on your data.
Okay. I have a more general questions about all these toolboxes. I don't develop any toolbox. I just use NIRS for psychology questions, but I've seen many toolboxes appear over the years. There's also now the Lion-NIRS from Montreal, and many toolboxes, and I'm wondering what's really the point of all, like literally every lab is putting a toolbox on GitHub now, and you know, which one should you choose and why?
Let me see if I can answer that question. Near-infrared spectroscopy and imaging is still relatively new, and there is many labs who are developing systems and developing algorithms. The reason that we are all putting our analysis tools and software available to everybody is simply because we are still trying to come up with the standardization that will bring the whole thing together. And the fact that we are making this available is working towards that. So now we have the fMRI data format, so all the software should be able to read it, and we are gradually getting there. My advice to you is choose one, and it doesn't really matter, just choose one. I think the key here is that if you choose one, you feel comfortable with what it's doing, and you analyze all your data using the same methodology, then you have pretty much good confidence that you are comparing like with like. But as we get better, then there will be standardized libraries made available to you.
Okay.
So
sorry.
Yeah, use Homer, use Neurodot, use Analyzer. Just the key is just to pick one and just use that.
Yeah. Well, I've been using Homer too, because when I started, that was the only one. But I was wondering, well, first, does Neurodot use the SNIR format as well?
It does take it as an input, yes.
Okay.
And it can make it as an output as well, yes.
Okay. So, well, I'm not using DOT specifically because I work on very small patients and I'm asking yes or no questions, so I'm not doing any mapping. I have the feeling that people are really going to these more sophisticated toolboxes because they allow something really cool in terms of mapping the brain. I think maybe what was missing for me this morning is, you know, information on where people would go, which toolbox they would choose for very specific applications in terms of brain mapping, that sort of things. It's just a feedback, sorry.
Yeah, no, that's a really important question. I'm glad that you bring it up. I don't know, Kiara, if you want to comment on just the choice of toolbox towards the question at hand.
I think, as Zamit said, like like, are you asking specifically about which toolbox to use to do mapping on infants? Is that your question?
No, I'm not. No, it's not my question. It's not a question. I think what I want to say is that there are so many available now that my students, they are having trouble trying. They try virtually every toolbox on MATLAB, and it's very long. And I think that just like you started in your presentation by showing, okay, maybe Homer for pre-processing, and then you go to another one for something like that, I think that you should perhaps make this more explicit, more detailed, and go through all the toolboxes. I think I can count almost 10 right now. So I'm just, it's not a question, I'm just saying it would be helpful for me if you could do that maybe next year or something like that.
I'll take that into account.
Thank you anyway.
Yeah, I think that's a really important point. I really appreciate your comment. I think there is a push to do more of those comparative studies in the community, and I know that people like John Spencer and others are publishing papers that are very specifically comparing how different processing routines lead to different answers with the same data and the same questions. And it may be something that is being addressed, for example, at the Society for fNIRS in October in Boston. Might be an opportunity to have more on that conversation. And, you know, I think this was the first from our community to present in this environment at HBM. And I think, you know, there's a lot of opportunity to expand the conversation with more of that perspective and bring in more of the other developers potentially as well next time around at the next HBM.
Okay, I'll wait for Boston then. Thank you.
Thank you so much. Yes, please.
Hi. It's a very new big question indeed. I'm trying to enter deep on the field. I've been working a long time with MRI and fMRI, all of this stuff, but I'm trying deep right now in infrared. So my question is going to be very, very related to things that I was wondering to see more. It's like, what are your experience around real-time NIRS? And the second one, besides the machine learning stuff, it's like if you have any other kind of experience with simultaneous NIRS and EEG devices.
So the first question is, sorry, the first question, what's the first question? Real time, yeah. So as we mentioned, the BCI system, that's the real time, and they did the evaluation. So that can be done as which, yeah, so that's definitely can be done. And nowadays they have so many commercialized device also allow us to simultaneously record both signals. Yeah. And what's the second question?
The second question, it was, well, let me just argue a bit about this, because the physiological signal, it takes around 12 seconds or some kind of seconds. So how can this be considered real time in
I got your point. You see, the real time is I got this is not the exactly real time, but maybe waiting a few seconds and get the feedback. So that is maybe in your mind is not a real time, right? So I get it. Yes. Maybe some solution can be used moving time window can solve that question. Maybe, yeah. Still have the delay. I agree.
This links to the second question, which is simultaneous with EEG. If you have some kind of experience with EEG coupled with the NIRS, because EEG has a kind of very fast neural activity. It can be registered to the point that we don't know where it is and where it comes from. Okay, we can use some kind of techniques to recover the place where it comes, what may come from the signal. But the point is that if you have some kind of experience, a coupling or putting together NIRS and EEG.
Yeah, as we mentioned, mentioned in the fNIRS informed the EEG modality. So in that case, I said, so we definitely get the time domain information in the EEG. That's super good. Yeah, but in the fNIRS informed the EEG, we also can get some structured information. So in that case, maybe a little bit slow, but we provide two kind of the modality information for the system. That's made the system maybe more robust, strong. Yeah, so that's somehow maybe also improve the classification accuracy. So that's the terms we can use both modality. Is okay for your question?
In terms of the gap, you put both electrodes and optodes together.
Yeah. So far they have, JTAG. They have the commercialized device. So they put the EEG and the fNIRS together in the same cap, and you're able to measure both signals together. Yeah. Thank you for your question.
Yeah, and just to jump in there as well, there are a few labs that are very explicitly doing development of truly simultaneous EEG fNIRS, right? So David Boas's group at BU has a really elegant paper that just came out a few weeks ago on that system that was discussed in the PNAS paper I talked about at the beginning. And then also Jana Keinersdorfer at Carnegie Mellon is working with other groups there, Ted Huppert and others, who are working on algorithms that are investigating a lot of what you're talking about in terms of what kind of the ideal combination between the fNIRS, which gives better spatial localization, how it may be able to help train the models that will then be utilized for the more real-time processing of the concurrently recorded EEG, right? That has the better temporal resolution, as you're saying. So on top of that, I would also highlight that there's been a lot of interesting work showing that the kind of envelope of the high gamma activity is actually a lot slower, but has a lot of potential. High gamma is up in like 80 and higher hertz, right? Whereas the envelope is more around 10 hertz and has actually a remarkably large amount of information content with it. And so that may be available to some fNIRS strategies frequency domain or time domain or other kind of like fancy ways of getting about maybe potential changes in the scattering signal. And so I think there's opportunities out there just beyond where the field is right now that may be able to get more access to the real-time data, both with optical as well as with optical combined with EEG. And then the last thing I would add is just that, as we were talking about earlier, if it's a model-based, when you utilize a really good model, you get a lot better information out of the data. And so pre-training and optimizing that model, all of the other stuff that happens after that is extraordinarily fast matrix multiplication. So it could be just a limited amount of time training an fNIRS EEG system with the right models, both the reconstruction model as well as the machine learning models, may really do quite a lot down the road to lead to combined optical, electrical, BCI applications and other sorts of things. And our group and many others are working on real-time data visualizations to help really ensure good cap fit and good data quality. Again, much like Nico and others are doing in the MRI field on FIRM and other like real-time assessments of data quality to make sure that when you're there taking data, you're not just wasting everyone's time, that you know that you can get in there and get 10 minutes of good data as soon as you can. Yeah, really, really great question. Thank you. Any other thoughts before lunchtime? And again, we're all around, or we'll be around limited, or you can always email any one of us. We'd happy be to engage with you. All right, well, with that, I'd like, or do you have a question? Yeah, okay, we'll take one more question.
So you briefly mentioned about crosstalk before, and now I'm curious because in the ultra high density, when you have all these channels that are close together, how can you recognize whether you have crosstalk in your time series, and how can you take into account for that?
That's such a good question. How do you recognize when you have crosstalk in the first place, right? So the real answer, I would argue, is slightly more technical than I'd like to have to give. But the real answer is kind of like you have to look at you have to run a given system in a way where you can very clearly tell, like the way any of these systems work is they flash the lights in a certain pattern and the detectors are either gated or they're always on. And so usually, like everything that we've been talking about is at the level of after the very zeroth order, first order pre-processing, you have source detector channels that are already paired together. But before that, you have raw detector channels that then get decoded into source detector pairs. And the only way to really know how good the crosstalk of the system is to look at the actual decoded look at the raw detector channels and look at what the information content is at each time step to see what the amount of information from the correct source is compared to from all of the other sources, to see whether or not any of the light from the source that is on is basically leaking through the detector channels and being misassociated with the wrong source. That makes sense? So that's true in continuous wave systems as well as in frequency domain systems. It all just has to depend on how the data is, quote, multiplexed, which just is a fancy word for like the pattern of how the sources are flashed relative to when the detectors are accepting information. So if you have to look at the undecoded data and compare that to the decoded data to then see basically how many orders of magnitude of crosstalk are there. And ideally the crosstalk level is down within the noise floor and is fine. But it's very much like a system characterization level of thing to do that hopefully every system that's out there is giving, a pattern to the user that they could run this and it'll tell them what their crosstalk is. Because by the time that you get the data that's decoded, it can be very challenging to really know 100% for sure if the data you're looking at is truly crosstalk or is truly not crosstalk. Does that make sense? So if you're worried about the system you have, usually the best thing to do is to bother the people that built it and ask them how you can really make sure that the crosstalk is, however many dB below the signal level so that you know that it's okay. Because it's very, very, very easy to have more crosstalk than you think you do. Yeah, great question. If there's nothing else, thank you all so much for showing up this morning and listening to everyone. Thank you, Hamid, Kiara, Lisa, Emma, and Dalin. This has been a lot of fun, and hopefully and thank you again to the the OHBM organizers for letting us present. Hopefully we can come and do more of this next time around. Thank you all for your time.